Hello all, welcome back to the second video of lecture 13. In this lecture, we are going to understand how a simple idea of logistic regression can be generalized to deep neural network model. So let's start with the basic logistic regression model. So we have this data set which is yi and xi's. There are n samples, I is from 1 to up to n, and then zi equal to xi transpose beta. Okay, so xi transpose beta is zi, and then you have pi1 equal to this sigmoid function, and then with probability p you have y equal to 1, and probability 1 minus p you have y equal to 0. Now omega 1 is my beta 1, so this beta 1 is also omega 1. Why I am using omega 1? Because in machine learning literature generally we use the omega 1 as coefficient as a notation. In statistics literature we use beta as the notation for coefficient. So this is mathematical representation of logistic regression. This is mathematical representation of logistic regression. Okay, now what we do, we graphically represent this logistic regression using these graphical nodes and arrows. So we have p features x1, x2 dot 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 xp, and we have an intercept parameter. This is intercept, and these arrows represents the coefficients beta naught, beta 1, beta 2 and beta p. So what you have is whatever the coefficient times the feature, so beta naught plus beta 1 x1 plus dot 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 beta p xp, that is our z. That is what is our node. This is oftentimes we call it node. Okay, then this node goes through a sigmoid transformation called activation function. We call it typically activation function. In statistics we call it link function. Okay, in statistics what we call it link function. In machine learning we call it activation function. Same thing, boss, no difference, it's just okay. And then once we have, typically it's sigmoid type behavior, and then you get a p, and with certain probability p you say I'm observing y equal to 1 or y equal to 0. In typical machine learning literature they will say cat and dog. Okay, period. So this is the graphical representation of logistic regression or single node neural network. Now can I generalize this situation? So I had single node, this is my node 1. I don't have to just stick to a node 1. I can create a new node. This is my node 2. Okay, now this were coefficient betas, but what I'm thinking, these is a different nodes, so we are going to use a different color. These are gammas, so these coefficients are called gammas, so different weights. That puts me two different nodes, Z1 and Z2, and then they go through a activation function. Again, each of them will go through an activation function, or in statistics literature we call it link function. Okay, and then now we have S1 and S2, and then again I can consider a intercept parameter, then omega naught, omega 1, omega 2, that gives me the Z3, another node. Then from Z3, this is a node, and then from Z3 again another activation function gives me the P, and from P probability I get dog or cat. Okay, so this is my neural network. So I have, this is typically called input layer, this is typically called input layer, and this is typically called output layer, this is called output layer, and this is hidden layer 1, hidden layer 1, this is typically hidden layer 2, so this how these things get, sorry, this is hidden layer 2, this is activation function, so I have to, so this is not hidden layer. This is my hidden layer 2, this is my hidden layer 2, and eventually, and this is the activation variables after activation. So this is hidden layer 1 is with 2 nodes and hidden layer 2 is with 1 node, and from there we get the final output layer. So why in the neural network we put separate hidden layers and we add more hidden layers and more nodes in each layers and all these things? Because you see this puts a new engineered features. So Z1, Z2, Z3, these Z3, this is Z2, Z1, these are all engineered feature. You can see them as an engineered feature. These nodes are nothing but engineered features. They are giving lot of interactions between X1, X2 and XP, and these interaction effects create an engineered feature in a higher dimension. As a result, it's able to model non-monotonic behavior, non-linear, non-monotonic behavior, non-linear, non-monotonic behavior. So that is the purpose of neural network. So this is the mathematical representation of the neural network that we just presented above. This is the graphical presentation of neural network, graphical presentation of neural network, and this is mathematical representation of the same neural network with 2 hidden layer, and in the layer 1 there will be 2 nodes, and so this is my first hidden layer. Okay, so this is my first, so X transposes are my input layer. You can think of input layer. This is my hidden layer 1 with 2 nodes, and this is hidden layer 2, hidden layer 2 with single node. This is the activation function. Activation function, or known as link function in statistics. Okay, so this is link function and this is output layer. This is output layer. Okay, so you have a now graphical representation of the neural network. This is mathematical representation of the neural network, and these interactions gives you engineered interaction. This, if you carefully look into it, there will be a lot of interactions. So if we add nodes, one of the major problem with the neural network is explosion of parameter space. This is, you have to be very super careful. You have to be super careful that neural network very easily the parameter space can super explode. If you add nodes and layers without thinking, that may lead to the explosion of the parameter space. Check how many parameters do we have in logistic regression, which is single node neural network. So stop the video for 5 minutes, go back to the logistic regression. So let me just go back here, and how many parameters you see in a single node neural network. Okay, how many parameters you see? I hope you have figured it out by now. So let us check how many parameters you have. So you have x1, x2, xp. So you have p1 to p many parameters and one more parameters for intercept. So you have p plus 1 parameters. 1 parameters for logistic regression, which is single node neural network. Okay, let us now go and check how many parameters you have for neural network. This neural network with 2 hidden layers and 3 nodes. Can you identify it? So stop this video, pause this video, okay, and check yourself. Take 2 to 3 minutes. Try yourself and identify how many parameters you have in this neural network. So I hope you figured it out. Let me tell you. So here you have 2 nodes. From node 1 you have p plus 1 many parameters because you have p features and intercept. So from node 1 you have p plus 1. From node 2 you have p plus 1. Okay, so p plus 1 plus p plus 1, and then these 2 nodes activating, and you are getting s1 and s2, and so this is like 2 1 2 and then its intercept. So 1 2 3 plus 3. Okay, so 2 into p plus 1 plus 3. So if you use a logistic regression with p equal to 10, a single node neural network means you have total 11 parameters. 11 parameters. Now if you have a simple neural network with only 2 hidden layers, one in the first hidden layer you have 2 nodes and the second hidden layer only 1 node, then you have p equal to 10, so you have 22 plus 3, 25 parameters. Immediately 1.5 times a jump in the number of parameters. You can see, boom, your number of parameters just more than doubled. Previously it was just only 11 and now it is 25. Just you add one more layer with one node extra and that's it, you are done. So in neural network, your number of your parameter space can explode. So how many parameters do we have in a double node network? So question is then come 2. First question is, shall we add more nodes? Second question, shall we add more layers? And which will be helpful and which will be more dangerous? So the first thing we can try out, that we will not add too many layers, we will add only single layer, but only we will add as many nodes as possible in the single network. This is called typically shallow network, because you don't have much breadth. Okay, shallow but fat single layer shallow network. So what happens? So here is an example. You have sort of 3 features. So x1, x2, x3, and you have single layer network, single hidden layer network. But how many? Z1, Z2, Z3, Z4, Z5. Let us consider there is no intercept thing. So even for each node you have 3 parameters. So over 5 you have 5 cross 3, 15, plus here you have 1, 2, 3, 4, 5, so plus 5. So 20 parameters you are modeling. Now with the same 3 features, you just decide like, okay, I will go for 2 nodes, but 2 layers. With each layer will have only 2 nodes. Then how many? So you have x1, x2, x3, you have z1 and z2. So z1 has 3 parameters, z2 has 3 parameters, and then here you have u1, u2. u1 has 2, u2 has 2, and then finally p will have 2. So 3 plus 3, 6, 6 plus 2, 4 is 10, plus 2, 12. So deep network with more layer, with each layer with a less number of nodes, like only 2 nodes, is giving you less number of parameter than a single layer with too many nodes. And so that is the reason that deep learning neural network is more popular than your fat shallow network. Because if you have a fat shallow network with too many nodes, your parameter space may explode. But you have a deep network with quite a few layers, but each layer will have maybe 2 or 3 nodes. Then what happens? That the number of parameters stay under control, and that makes deep learning neural network very useful. It can capture the non-monotonic, non-linear behavior. Okay, it can capture those behavior, but at the same time your parameter space is somewhat controlled. That is a very useful feature of neural network. So the purpose of the neural network to discover the engineered feature automatically. So that is the main purpose. But as I say, even then my network can grow very fast and my parameter can explode. So if my parameter space explode, then what we can do, we can put a very tough L1 penalty to drop the features, or lasso penalty to drop the features, push them towards 0 and make it a sparse network. So make it a sparse network model. Okay, and then it is better to use deep network with couple of nodes in each layer, couple of nodes with each layer so that we avoid the explosion of the parameter space. So with this, I will stop here. So deep learning neural network is not really part of this course. This is a really advanced topic, but I just give you a sort of a glimpse of how deep learning neural network are being developed, and logistic regression or single node artificial neural network or single perceptron network models are the sort of a key building block for deep neural network models. So I'm not going to do deep neural network models in this course. You will get a lot of much better course. You should go and take a full course on deep learning neural network. So this video I just try to show you what is the relationship between simple logistic regression and deep learning neural network for binary classification model. Thank you very much. See you in the next video.